Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during this session. And if you have questions, please direct them to me, Paul Donahue, via the chat function. We'll do our best to answer those questions at the end and to follow up with any unanswered questions after the session via email. As I think you all know, these Tech Talks have been designed to provide straightforward insights into radio frequency components. We talk about the related technology and the extra design and engineering value that is added by a custom manufacturer such as Quantic TRM. To begin today's session, I am once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. Shaun is the author of 2 U.S. patents and a number of white papers and technical articles on passive microwave technologies. He's been with Quantic TRM since the late 90s, and his passion for the job and for solving problems has only increased over the years, especially when it comes to solving our customers' design and engineering challenges. So welcome, Shaun. Would you maybe like to share an overview of today's topic and your objectives for the session?
Certainly. Thank you, Paul. So for today, what we're going to talk about is SWaP-C. And we'll go ahead. First, we'll start with a definition of what it is. Then we're going to talk about what makes SWaP-C important and why we should consider it. We'll then go ahead and we'll expand the concept a little bit to talk about the whole idea behind SWaP-C and not just worry about the acronym. And then we'll go through some Quantic TRM differentiators and wrap it up with a summary.
Okay, well, that sounds great. So to get started, what exactly is SWaP-C?
All right, so SWaP-C is an acronym that's used in the industry, and it's a generic acronym. And what it really means is that size, weight, power. When you compare size, weight, and power, and what's the cost of doing that. So when you think about the bigger is better, or smaller is better, or gee, it handles more power. Those are the sorts of things that you talk about, and it is sort of a generic sort of way of looking at things. And the last thing about that really is the cost. Everything comes with a cost, and as we go through and as we start looking at these devices, what is the cost of making it smaller? What is the cost of decreasing weight or increasing power? So really, this tool becomes a way of looking at the sort of inputs to the design as far as what's important to the customer and what is the customer willing to pay for. And is the customer willing to pay for these additional features or making it smaller? For example, if you're looking at a device that's going into a very large system, say, for example, it's going on a shipboard system, and it's a very large, in the middle of a very large rack. Getting a component from some small connectorized device and taking half an inch off of the diameter of something or other in the part may not add any value to the customer. And if making it smaller adds cost, that may actually not be a good thing. So SWaP-C is a way of taking all these parameters and weighing them against each other and say, well, gee, is this something that the customer wants? And is it something that the customer needs? And is the customer willing to pay for it?
So are there any key reasons or, history, how this type of analysis was evolved and why it's so important?
Sure. So whenever you're going in and doing design work, it doesn't really matter what you're designing. There's always a trade-off, especially when you get into the realm of passive microwave components. You're always dealing with the laws of physics. You're talking about, for a lot of distributed elements, you're looking at wavelengths. You're looking at how many sections that you need to design a transformer to get the bandwidth in. And as you're going through all of these sorts of trade-offs and trying to figure out what is the best VSWR you can get and whatever that performance metric is, very often, as you increase one of those or make one of those parameters better, it's not always an across the board win for everything. And you have to go through there and actually be very careful as you're evaluating these individual parameters to make sure that you make the right choices so that what you end up with is a part that the customer wants and needs in their system, and also what is the customer willing to pay for it. So really, as you start going through and start looking at these sorts of parameters as a designer, what you need to find out from the customer is what is really important to that system. Is size the most important? Does it have to handle a lot of power? Or does it need a lot of bandwidth? Or what are these questions? And once you know what the customer really needs for implementation in the system, that then starts to set up the criteria for really what it is that you want to use as your design criteria in making all of his associate trades.
Okay, so you've talked about the impact on the overall system. Is this approach, the SWaP-C, is it applicable only to the overall assembly, or does it apply to multiple parameters or aspects of the design?
Yeah, no, so it applies to everything, and I just kind of just hinted at the slide here in talking about the previous one. Really, I think as you're going through the design process, every parameter is important. It's not just how big it is. It's not just how much it weighs. It's not just how much power that it can handle. But it's also when you get involved with designing anything, it's how much bandwidth you have, how much insertion loss you have, what is the VSWR, and so on and so on. Within networks, for example, power is not always, you don't always want a part that handles a lot of power because power and size very much are opposite. When you get a part that handles, say 10 kilowatts, it's going to be a part that's going to be a very large part. It's going to occupy a large portion of your desk. Whereas if you get a part that is designed to handle down in the milliwatt range, well, that can be a very small component. Something that you can then integrate into a system quite easily. So, higher power, always comes at a cost, and you have to look at that size versus power trade-off. Those same trade-offs happen. For example, for bandwidth, say if you are working at X-band, as an example, and you have a part where you're doing an up-downlink system, and you need a directional coupler for some power sampling, but you only need a couple hundred megahertz bandwidth. You're not going to want to use a 2 to 18 gigahertz coupler, because as you go across that sort of frequency range, you're going to have to have multiple sections to cover that, as opposed to a single section that you can do and still cover your needs. Your insertion loss will be much higher. Your chances are your VSWR won't be as good, and it's certainly going to be a lot larger and a lot heavier. If that part is going on something like a spacecraft, then the broadband part is actually a detriment because of the other parameters that it affects. So it's really important to consider as you're going through your design analysis, when you're speccing your subcomponents, be cognizant of what is really important to the system and what does the system really need. Very often, we always like to put margin as system designers into our budgets. And very often those margins come with a cost, and we just have to realize what that cost is. It's not always money. Sometimes it's performance cost.
Well, makes sense. Good information as always. Maybe you'd like to summarize this concept?
Sure. So basically, SWaP-C is it's a generic term used, size, weight, and power, and versus cost. But what's really critical here is to understand what performance parameters are important to the customer. What is it does that customer needs? And then once you understand all of those trade-offs that you have within the customer, will the customer have a budget to support really what's important? and sometimes looking for the holy grail of what we have from a design may come at a very high cost that won't that the customer system just simply just cannot afford, and therefore we have to be careful of all those trade-offs going through to make sure that the part that we design the customer can afford and does the job that they need and fit in the system.
Okay, thank you. And what are some of the unique aspects or differentiators that Quantic TRM provides in this area with respect to SWaP-C?
Certainly. So really what I think one of the big differentiators with TRM is we like to talk to our customers, and we like to work with our customers to make sure that the part that they've requested will really do the part that they need in the system. And by having that conversation, we can then go beyond what's written on the data sheet to make sure that the part that they get is really the part that they need. We have to understand really what the focus of the system is, and whether it is very often going through a sort of design trade-off, whether or not insertion loss, for example, is paramount to the system, or whether it's return loss. Those sorts of things not only design the topology of the circuit, they also define these sort of substrates that we use, for example, the environment that it's in. Again, all these things really help drive each other, and very often that they're counter purposes. So sometimes, there isn't the one thing that's the best for everything. So we have to go through, and as we go through those trades, like SWaP-C, we have to go through there and make sure that what we select is the best for the customer for this project. And like I said, we like to work with our customers to make sure that that all those needs are met.
Okay, and we do have one question, Shaun, and it does, I think, kind of align with the trade-offs that you just mentioned. But the question is, does any one of the variables in SWaP-C tend to stand out or outweigh all the others?
I think they're all important. I think there really is no one that's the most important. However, there is one overall thing that sort of drives everything, and that is can the customer use it in their system? It doesn't matter if it's the greatest thing in the world. If it doesn't have a use, it doesn't have any value. So it has to meet the customer's needs, however we get there. And that's really the bottom line. Like I said, we can go ahead and we can design the best thing on paper, have the hottest thing in the market. But if it doesn't fit the customer's needs, it doesn't add any value to the customer's project. It doesn't do the customer any good. So it's really important to listen to the customer, make sure that the part that we're delivering is what they need. And that, I think, is the most important part of SWaP-C for this over here, is to make sure that the customer's requirements are met.
Okay, well, thank you, Shaun, and thanks again to all of you for joining us. In conclusion, I think the bullets on your screen say it all. And going forward, if you are a customer and have more questions, or if you'd like to discuss details with one of our engineers, we'd love to hear from you. Please feel free to call our engineering hotline. The number is on your screen, 888-677-6877. There are no costs for these calls. And if you're one of our field sales representative, then you know your calls are always welcome. You can also submit questions directly through the sales rep portal on our website. In case it's helpful, our next Tech Talk is scheduled for Tuesday, April 25th at 1 p.m. Eastern. And the topic will be Next Generation SIM Feed Networks. Thank you all. Thanks, Shaun.
Thank you.